Okay, so now we want to discuss surface integrals. And I'm not going to do all the details. I'm going to kind of trace the ideas that we had for line integrals and hope that you can believe some of the things I say because they really go along the same lines. We don't have the time to do all the details for everything. So S is a surface. S is a surface given by a parametrization R of uv, which is x of uv, y of uv, z of uv. So that's the parametrization, where u and v belong to some domain D in R2. So that's a surface. And there's another ingredient now. There's a function. F of x, y, z is a function, a scalar function. So it just takes scalar values. It's a function from R3 to R. And the surface integral of f is defined. So first of all, it's written, the integral. It has a double snake. It's over S, okay? And it's written of f of x, y, z ds. Okay, so this is how it's expressed. This is really meaningless. You can't do anything with this. This is just a shorthand notation for it. But what it is the double integral, and now this is a regular double integral, over the domain of the parameters d, du, we needed a lot of space, du dv, so this is now a good old double integral of the function f evaluated on the parametrization, so f of x of uv, y of uv, z of uv. And here I'm going to throw in the length of the normal, Ru cross Rv, and this is it. Let me make this huge D somewhat smaller so I can write here what this is analogous to. So first of all, this is just the length of the normal, this Ru cross Rv. And you should see, well, this S is rather big as well. You should see that this is analogous to the line integral of a scalar function. Let's write the line integral of a scalar function, f dr, remember this? Over some curve gamma was given by the integral dt, where t were the parameters, t was the parameter, and it ranged over the domain of the parameter, which is some interval ab, but for a single variable integral we usually write like this, of f calculated on the curve, so f of x of t, y of t, z of t, and then what did we multiply by here? R prime of t, length. So this is the line integral of a scalar function, and you should see the analogy. Clear? Moreover, the physical meaning of a surface integral of a scalar function, the physical application, or the one of them, a common one, is suppose you have some density described by f, mass density or charge density or whatever, then the total mass or the total charge of the surface whose charge or mass density is given by f would be this. Okay, so let's write that physics charge or mass of S with charge or mass density F. Okay? Okay, it doesn't depend on the parametrization that you choose. That is not a trivial fact to see. I'm just telling you that. It wasn't trivial in any of the integrals that we did that required parametrization, and we never went through the formal proof. And let's do an example. So example, suppose, so let S be the part of the cone z equals the root of x squared plus y squared. So this is a cone. This is an upside-down clown hat that we've already discussed several times. But I don't want all of it. S is going to be only the part of the cone that lives above the circle x squared plus y squared is less than or equal to 2x. We'll try to draw this in a second. Okay? And the function f of x, y, z is going to be x squared plus y squared plus z squared. And I want to find so suppose this is the surface and this is the charge density, and I want to find the total charge of the surface, whatever. So we want to find the surface integral of f ds, where this is f. So what do we need to do? By definition, we need to parametrize the surface, and then calculate the normal, and then find f on the parametrization, multiply by the length of the normal, integrate du dv for the parameters. Okay? Looking back here, this is what we want to calculate. Good? So the first thing I need to do is find the parametrization of that surface. Usually that's the hardest part. Well, sometimes calculating the integral is not that easy, but usually finding parametrizations whenever the surface is not trivial is not trivial. Okay, so let's find the parametrization. Let's figure out what this surface is. So why is this a circle? Why is this a circle? Well, let's rewrite it. Okay, so x squared plus y squared is less than or equal to 2x. I want to rewrite it. I want to complete the square and rewrite it in a standard circle form of equation. So I can rewrite this as x squared minus 2x plus y squared is less than or equal to 0. And completing the square would add a 1 here. Let's take a different color. So I'm going to add a 1 here plus 1 to complete the square. And then I'm going to add a 1 here. So what I get is x minus 1 squared plus y squared is less than or equal to 1. Good? So this is a circle. Now you can see that it's really a circle, right? Of radius 1, centered not at the origin, but rather at 1, 0. Do you agree? Everybody? Okay, so let's draw S. S is a part of the cone that only lives above this circle. So here is a picture. This is x, this is y, and this is z. The cone, why do I have two blues here? I'm having the blues. Here's the cone. This is the cone. And down here, let's take another color. Down here is the point 1, 0. It's somewhere here, let's say. So this is 1, 0, or 1, 0, 0. And there's a circle here, so this is the negative y-axis. And we're looking at a circle at the xy plane, centered at 1, 0 of radius 1. So it's a circle on the xy plane, on the floor, whose center is this and radius 1. So it should be tangent to the y-axis here and look like this, except since we're in perspective, it's not going to look completely like a circle. It's going to look something like maybe something like this. But this is a circle. Do you agree? Okay, a circle of radius 1 centered at 1, 0, 0 on the xy plane. Now what is my S? My S is the part of the cone that lives above this circle. Okay, so if you think a bit, what do we mean the part of the cone that lives above this circle? If I were able to climb up here and look from above down like that, and only look at the part of the surface that lives above this red domain, right? It's not just the boundary of the circle, but rather the inside, right? This is the circle. What I would see, or you can think of maybe a flashlight coming from up here and only what's lighted here. So what I would see is something that would look, it would start at the origin. Remember, this comes out at us like this, so it would be something that looks something like this. I don't know if this is convincing. Okay, and this is part of the cone. This is okay, it's part of this cone here. Is that convincing? Okay, it's good? Everybody? Okay. It's not crucial to be able to draw it accurately. It's just because I want you to get a feeling that it's not totally mysterious. Okay? Okay, so this is our surface. This is S in orange here. It's the part of this cone that lives above. This orange needs replacement, and I don't have a replacement orange. So this is S. Good? Okay, so let's put all these colors aside and let's see if we can parameterize this. So, first of all, let's parameterize the cone, the blue. Okay, so the parametrization of the cone, so the cone is given by, we used U and V. I really want to use rho and theta. Let's use rho and theta. It doesn't really matter, but we're already feeling better with parametrizations of surfaces. So the cone is rho cosine theta, rho sine theta, and rho. That's the parametrization of the cone. Do you remember that? Right? We had it with U and V. U cosine V, U sine V, and U. Right? This example is following us since we started discussing surfaces. It was the first surface we parametrized, then the first surface we found the normal for, then the first surface we found the surface area for. Good? Do you still recognize it through the change of the names of the parameters? Okay. And so these are all the points sitting on the cone, where rho, well, it depends on how far up we go, and theta goes the entire circle from 0 to 2 pi. But we don't want all of these. We want only that orange bit, only sitting above this, above the circle. So the x and the y have to satisfy, the equation of the circle, right? So S, for S, x squared plus y squared is less than or equal to 2x. So what is x squared plus y squared? It's rho squared cosine squared plus rho squared sine squared. So it's rho squared. And that should be less than or equal to 2x, 2 rho cosine theta. Do you agree? Good? And I can cancel out one of the rows here. So I get rho is less than or equal to 2 cosine theta. So there's an additional requirement on rho and theta in order for us to get only points above this circle. And there's one more thing. There's also a limitation on theta. Okay? For the entire cone, theta could range from 0 all the way to 2 pi. Theta is the angle to the positive x-axis, right? For this part, what does theta range from? Remember, theta equals 0 is the x-axis. We're only looking at points that are on the front of the y-axis. So theta could only range from minus pi over 2, 0, to pi over 2. Do you see that? And theta is bounded between minus pi over 2 and pi over 2. Only thetas from here to here live in this. S lives only for those thetas. Clear? Good? Okay, so this is our parametrization. These are the requirements on rho and theta. This is the domain D that rho and theta belong to, and this is still the parametrization. It's all points of this form where theta and rho satisfy these two things. Clear? Okay. So now we can calculate the integral. So the integral over S of f ds equals the integral, and now I want to write it right away as an iterated integral. It's a double integral. I want to write it as an iterated integral. Theta is bound between two constants, and rho is more is related to theta, so this has to be the outer integral, right? So I'm going to write from theta equals minus pi over 2 to theta equals pi over 2 d theta of the integral. Rho is always positive, right? Rho is the distance to the origin. I can add here that it's always positive. That's why I could cancel out and everything. So rho goes from 0 to rho equals 2 cosine theta. That's the range for rho, d rho. And now I need the function. The function was f of x, y, z was x squared plus y squared plus z squared. That was the data for this example. So x squared plus y squared plus z squared. X squared plus y squared is rho squared plus z squared plus another rho squared. So there's a 2 rho squared here. So this is f of x, y, z evaluated on the parametrization. And what do I have to multiply by? Not the Jacobian. Hint starts with n. The normal, right? We're not changing variables here. It's confusing. So the normal, and I'm not going to calculate it again. We saw that the normal for this parametrization was root 2 times rho. Remember that? It was root 2 times u when rho was u. Okay? So this is going to be root 2 times rho. And this is the integral that we have to calculate. Good? Okay, let's calculate it. So I have a 2 root 2 that I can throw out, and then I have a rho cubed here. Antiderivative is rho to the power 4 divided by 4, right? So let's write that. So this equals the integral from minus pi over 2 to pi over 2 d theta. And then I have, well, I have the 2 root 2. This is the scalar that bounced out of the snakes. And then I have rho to the power 4 divided by 4, evaluated between rho equals 0 and rho equals 2 cosine of theta. Good? So plugging in 2 cosine of theta, so there's the 2 root 2 here. Plugging in 2 cosine of theta, I get the integral from minus pi over 2 to pi over 2 cosine theta to the power 4 times 2 to the power 4 divided by 4, which is just 4. So I get a 4 here, and then a d theta. And the snake turned out to be too big. Good? Now I can throw the 4 out. So I get 8 root 2, the integral from minus pi over 2 to pi over 2 of cosine to the power 4 of theta d theta. The second half of this entire course boils down to calculating Calc 1 integrals. Okay? If you have a gap there, if you're not feeling completely secure with calculating Calc 1 integrals, single variable integrals, that's something you should figure out, something you should practice a lot. Take a day off. Do nothing but practice single variable integrals. Otherwise, you won't be able to get to the end of a single Calc 2 sort of problem. Okay? They all eventually end up as single variable integrals. Okay, so how do we calculate this? I'm not sure I want to write all the details. Do I want to write all the details? Nah. Okay, so what you're going to use here, I'll tell you what it ends up being, providing I did it correctly. I got ... I got 3 pi over 8. You can verify that. So what you use here is the formula for cosine squared. Cosine squared is 1 minus cosine. Let's write it. Use cosine squared of x in general is 1 minus cosine of 2x divided by 2. Or 1 plus or minus? I think it's a plus here. Okay? This is what you need to use. And you're going to use it a couple of times because you have cosine to the power 4. So first of all, you'll write cosine to the power 4 is 1 plus cosine. You're going to break it up a couple of times. Okay? Then you're going to get cosine squares here, and then you're going to do it again for each of those. Okay. Yeah, and then it becomes it's a couple of lines here to calculate it. Good? Questions? Okay. So that's this example. The next thing we want to do is define surface integrals for vector-valued functions, for what we called vector fields. And that's going to have a physical meaning, which is something we haven't encountered yet. It's called the flux. We'll discuss that in the next clip.